Okay, this is exam 3 for Physics 102, Spring 2015. First, consider this circuit. Which of these equations is correct? Okay, well, let's just start with this one right here. I have I1 plus 4. So I1 has to be along here, and it has to be a 1 ohm resistor. But I don't have one of those, so I'm just going to go and cross that out. Because I1 is along this branch, and there is no 1 ohm resistor to give us this I1. So the rest of it I don't even need to worry about. Here I have 2 minus 2I1. So that means I'm going in this direction. Minus 2I1, that's correct so far. Plus 8. Oh, that should be minus 8. And then that would be equal to 0. That would be correct. Let's see. Next I have I2 plus I3. I1 plus I2 equals I3. There's I1 and I2 are both coming in. Oh, and I3 is also coming in, so it should say plus I3 equals to 0, so that's not correct. And then hopefully this last one is correct. I have 2 minus 2I1, so far so good, minus 4, that's right because I'm going from high to low, plus 2I2, that is correct because I'm going with the current, or excuse me, against the current, so that's positive. So D is the right answer. For the circuit, what is the direction and magnitude of I2? Well, I want to find, let's delete all this. I want to find the current here, I2. And so I'm going to imagine using this loop because there is no resistor in the I3 part. So I3 isn't going to be a variable in that equation. So I'm going to write the equation. I'll start right here and go in this direction. So that is going to be 8 minus 4 plus 2I2 equals 0. And then if I solve this for I2, I get negative 2 amps. So it's 2 amps. It says that it's down, but since it came out negative, that means that I2 is up. This multi-loop equation, or excuse me, this multi-loop circuit has 6 distinct currents. Which of the equations is correct? This one was a little bit different than one we've seen before because I have this extra branch here. Instead of having 3 currents, I have 6 currents, but application is still the same. I just take each junction. So we have I1, I5, and I4. Let's see, I1, I5, and I4, they all come into this junction. I1 is going out, I5 is going out, and I4 is going out. So to make this correct, this would say plus I4 equals 0. So A is not right. I1 minus I2 equals I3. Let's look right here. I have I1 and I2 coming in, and I3 going out. So if this were to be correct, it would say I1 plus I2 equals I3. So that was not right. I2 plus I6 equals I5. Let's clear this up a little bit. I2 plus I6 equals I5. That's right here. I have I6 and I2 going out and I5 going in. So it should say I5 equals I2 plus I6. That is what it says. So C must be the right answer. Let's go and look at this last one. I3 plus I6 equals I4. I3 here. I3, I6, and I4 are all going in. So this should say plus I4 equals 0. So C is the right answer there. Which of these plots show the current versus time for a charging capacitor? Well, charging shows the current, rather. Current is V over R. That's our maximum current. And when it's charging, it will have the maximum current right away times e to the minus t over RC. So initially, our current is going to be equal to this maximum value. That gets rid of this one, right? Because that initially has a current of 0. And it's an exponential, so it's not that one. And it's also not this one. So A is the right answer. That's just how it looks for that exponential function. Consider this RC circuit. R equals 1 mega ohm, C equals 5 microfarads, and E equals 30 volts. What is the charge after 10 seconds? Well, first let's just find tau. Tau is equal to RC. This is our time constant. That's 1 mega ohm, 5 microfarads. That's 5 seconds. And then if I want to know the charge while is it charging here? Yeah, it's charging because initially it has no charge. This is going to be equal to Q max, which is C times V times 1 minus e to the minus t over RC. All right, that's equal to C times V 5 times 30, that's 150 microcoulombs times 1 minus e to the minus 10 over RC, which is our 5 seconds. That's our time constant. All right, and let's see. If I do this, I get 150 times 1 minus e to the negative 2. That's 0.1353. I get 130 microcoulombs. Consider the RC circuit. In the previous question, how long will it take the capacitor to fully charge? Well, I know our time constant is 5 seconds, so it's going to take 10 times that amount of time, because the time to fully charge is 10 tau. This is a true statement. A monopole does not exist. Which of these is the best reason for why this is true? Moving electrons cause magnetic fields. Just to remind you, it used to be people thought if I had a north and a south pole and I split it up, I'd get a south and a north. And then if I keep splitting it up, eventually I'd get a north and a south pole separate. All right, but that doesn't occur because this magnetic field is caused at an atomic level by moving electrons. And you're not going to split those electrons up. These other statements are true, but that's not the reason that a monopole does not exist. This figure shows a wire between the poles of a magnet. The location of the wire, what is the direction of the magnetic field? Magnetic fields always run north to south, so it's going to be to the right. And then also, regarding that, consider that figure. What is the direction of the force on the wire? So our wire was coming out of the page. That's our current. And I want to know what is the force. The magnetic field was in this direction. So let my fingers go in the direction of I. The magnetic field is to the right, so my palm goes towards the right, and that tells me that it's up. Current goes around this page in a clockwise direction, so imagine this is your page. There's a current going around in this direction. If I do my right hand rule, I can find the current here. Let my thumb go in the direction of the current. My current, or my magnetic field, will be into the page, out of the page, and then over here, into the page, out of the page. So in the middle of the page, it will be away from you. This is very similar. I have a point that's equidistant between two long parallel wires. What is the direction of the magnetic field at point A due to the two wires? So here I'm going to have a magnetic field due to both wires because they have the same current and because I'm the same distance from both. The magnitude of those magnetic fields are going to be the same. Two magnetic fields with magnitudes the same. Here I have a current that's down. That means on this side I'm going to have a magnetic field into the page, and on this side out of the page. So in the center here I'll have a magnetic field into the page. Here I have a similar thing. I'm going to have a magnetic field into the page and a magnetic field out of the page. So over here I'll have a magnetic field out of the page. These two add up to give you no magnetic field at all. A 2 coulomb charge is traveling 12 meters per second in a magnetic field that is orthogonal to the velocity and has a magnitude of 3 Tesla. What is the magnitude of the force on the electron? All right, well, F equals QVB sine of theta. Theta is 90 because it's orthogonal, so that means this sine of 90 becomes 1. So this is a simple problem. I just have 2 coulombs. V is 12 meters per second. And B is 3 Tesla. That's 72. By the way, these are not realistic numbers for a charged particle. I mean, I suppose you could maybe make this some way, but not likely. Like if we're talking about atomic particles, they're going to have very fast speeds and very small masses. Okay, so our forces are actually going to be quite small in these. If you put a 72 Newton force on an electron, that baby's moving. All right, you're going to have a really fast acceleration. You know, what, 10 to the 30th or so. So I just did those numbers to make them easier for y'all, because I'm that kind of guy. All right. All right, let's see here. I have a positive particle that's approaching a current carrying wire is shown. what direction will the particle go? All right, well, first of all, let's imagine our magnetic field here. I get a magnetic field going into the page and out of the page. So this thing, this particle, is coming into a magnetic field in a region that is out of the page. Now, I want to know what is the direction of the force on this particle. Well, velocity is down. The magnetic field is out of the page. So that means that the force acting on this is in this direction. So it's going to cause this particle to follow a path that's like that, a circular path in that direction. So what's that? That's to the left. This loop of wire, which sits in a B field, directed to the right. So if you got that question wrong earlier, here it tells you your magnetic fields run from north to south. As a direction shown, the current in the wires as shown. What is the direction the loop will turn? All right, so let's just take this left side first. I have a current into the page. I have a magnetic field in that direction, and so current's into the page. That means that my force over here will be down. That will cause this thing to go in this direction or counterclockwise. By the way, if I do that also over here, my force on this side is up. So I will get it to move in a counterclockwise direction, at least for a half turn, at which time it'll flop back. Which of these statements about a magnetic force on a charged particle traveling through a magnetic field is true? All right, the magnetic force is a centripetal force. The magnetic force is a centripetal force. That is a true statement. The magnetic force is always perpendicular to the velocity. That's also true because it's a centripetal force and because it's orthogonal. That is always orthogonal to the velocity. The force is always orthogonal to the velocity. The magnetic force always causes circular motion. Hey, that's a true statement too. So E is the right answer. Current of 30 amps is in a circular loop with a radius of 0.1 meters. So I have this loop of wire. It has 30 amps going through it. It has 10,000 turns of wire, and its radius is 0.1 meters. I wanted to know the magnetic field generated by this loop. That's going to be mu naught I over 2R N, actually, times the number of turns. That's going to be 10,000. Mu naught is 4 pi times 10 to the minus 7. I is 30 amps divided by 2R, which is 2 times 0.1. Let's see here. I'll get rid of this here. That's a 2. I'll get rid of this and make this 100,000. You could do this however you want, but I have 200,000. I get 1.9 or 2 Tesla is the right answer. Positive particle moves in a B field of a mass spectrometer. The magnetic field is 8 Tesla. It has a speed of 4 meters per second, and the radius of the path is there. I want to know which of these particles is it. I give you your mass and your charge. So you're going to find the mass to charge ratio. Let's see, I always forget what it is. I'm going to say QVB equals mv squared over r. You had the cyclotron equation on your equation sheet, but I always forget what it is. So I'm going to have m over q is br over v. B is 8, R is 0.5, divided by V, which is 4. That's 4 over 4, which is 1. So my mass to charge ratio is 1 kilogram per coulomb. This is the only one that has a mass charge ratio of 1. This is a mass charge ratio of 2. This is 4, and this is 16. So yttrium is the right answer. Organize these in order of shortest to longest wavelength. Well, I know the shortest wavelength is gamma rays, so that gets rid of these. And I know the longest is radio, but so that could either be here or here. So it's really, which is a longer wavelength, visible or infrared. Infrared is a longer wavelength, so let's see, I'm going from shortest to longest, so that would be D is the right answer. Which of the following statements is true? Okay, Newton believed light was a particle because of reflection. That's true. Einstein showed light was a particle through the photoelectric effect. That's true. Huygens believed light was a wave. He did believe it was a wave, but not because of interference. He thought it was because of refraction. So that's not true. And Young showed light was a particle. That's not true. He showed that it was a wave through the double slit experiment. In fact, it was through the double slit experiment that he showed that it was a wave, but we used a different term. We called it interference. But because it should be wave here, so that one's not true. 1 and 2 is the right answer, C. This following figure shows a fiber optic cable has a core and a cladding with a certain index of refraction. Which of these statements must be true about these indices of refraction? Well, in order for this to occur, for total internal reflection, this index has to be bigger than this index. So A is the right answer. Just to remind you, let's say I'm doing glass to air, which is a common thing to do, like with fiber optic cables. I need it such that it's going to bend away from the normal, and that will only occur if this index N2 is smaller. So that's A is the right answer. The index of refraction is 1.8, and for air it's 1.0. The critical angle, what is the critical angle? So here I'm going from, it says from benzene to air. Benz, all right, going this way, this is 1.8. This is an index equal to 1. I want to know what is the critical angle. I know that this angle has to be 90, so it's going to be 1.8 sine of theta equals 1 sine of 90. And then I solve this for theta. I get 34 degrees. All right. A ray of light strikes a thick glass sheet at an angle of 25 degrees with the normal. It's in air. It's a ray of light. So I'm going from air to glass. It's going in this direction. I have 25 degrees here. Find the angle of the refracted ray within the glass. First of all, I know that it's going to go in this direction towards the normal, and that this angle will be smaller than this angle. So you know what? I don't even look at all this. I can just tell you the answer is 16 right off. But let's go ahead and do this. I have 1 sine of 25 equals 1.5 sine of theta. If I solve that for theta, that's the inverse sine of sine 25 over 1.5. You'll find that that's 16 degrees. You can try that on your own if you like. All right, when light passes from air to glass, it bends. Which of these? Well, we just did this from air to glass. It's going to bend towards the normal. But why does it bend towards the normal? It bends towards the normal because it slows down when it enters the glass. All right, light travels through 3 media as shown here. Where does light travel the fastest speed? Well, let's take medium 1 and 2. I like to draw my little wave fronts here. I know then in order to move in this direction, it has to slow down. So that means that V2 is less than V1. And then, traveling in this direction, it speeds up going in this direction. So that tells me that V3 is bigger than V2. All right, so V3 is bigger than V2, and V1 is bigger than V2. So I know it's not medium 2. It's either V3. Medium 1 or 3, and I also know it's not D. I want to now look at medium 1 and 3, so this will be medium 1 and medium 3. What I'm going to do here is I'm just going to get rid of this medium 2. I can draw the ray as it appears up here, and then draw the ray as it appears down here, just bypassing medium 2 altogether. Draw my wave fronts. That means it has to speed up when it goes into medium 3 to bend that way. So that means that V3 has the highest speed. All right, and one last one. What is the angle of reflection off of mirror 2? All right, well, I know that this angle is going to be 30 because of the law of reflection. That makes this 60 and this 30 because this is a triangle. And if that's 30, this has to be 60. That means that this angle is also 60 by the law of reflection. So 60 is the right answer. All right, here's the solutions.